you how to do linear regression using ordinary least squares. So that's standard and typical linear regression. And then I will show you how to do the same using Bayesian linear regression using the RStan package. Needless to say, I will be doing this in R. So in order to run this example, you need to install Python from www.python.com, and you can install it for Windows. You also need to go into the following GitHub repo over here and download Bayesian_versus_linear_regression, which is the example that I will be using. Remember to also download the CSV file over here. Let's get started. Doing linear regression in R is quite simple. Essentially, we will use a function called LM, which stands for linear model. So let's see how we do this in this example. So the reason I chose Python for this is that it allows me to drop my code into panels and then connect those panels and run things. And it is very nice when we are doing unrelated things inside or within the same project. As you can see here on the left, I have the linear regression using the LM function. And here what I have on the right part, I have the Bayesian model. So it's quite nice to see the two things disconnected. It really makes it really clear that we're doing different things here. In order to do this, I will load the data here. I will print a summary just to show how the data looks like. So we essentially have one variable that we want to, one target that we want to predict, total variable. And these are sales for a website. So we have whether the website was a standard type, blue type, or red type. So those are three experiments that we do on our website. And then we have a type there, that's a coupon. Or not coupon, so standard sale. And what we want to do here is basically to call the LM function. So LM stands for linear model, so total, we will be modeling that in terms of the website and the type. So these are two categorical variables. This has three types, so website has three types, standard, red, and blue, and type has two types. And then I am doing a -1 just to subtract the intercept. If I want to keep the intercept, I will show you how we do that in a minute. So then I just run my model in here, and this is the result that I get. I get an estimate value, an estimated coefficient for each one of the parameters that I estimated, plus the standard error, the t-value, and the p-value. These p-values are very small, meaning that they are significative. You can see a significance codes here. So the 3 asterisks mean that the coefficients are significative at the 0.01 level. And the last thing that we typically do after we do linear regression using this approach is that we analyze the R-square. We say, well, is this model kind of working? Is the R-square high? So remember, the R-square goes from 0 to 100, so from 0 to 1. And it is the proportion of the variability in the data that our model explains, the proportion of the variability of the total variable of the target that our model predicts. So our model predicts pretty much all of it, which is very high. Usually on real scenarios, you will see this like being 60%, 50%, 40%, something like that. We usually don't care so much about this. This is an F statistic test, so it tests the joint hypothesis that all these coefficients are equal to 0 at the same time. Obviously that won't happen. You see a p-value small, and the reason I know that won't happen is because the t-tests individual are all of them significative. So yeah, that's really how we proceed. Then after we have this model, we can do inferences and we can do analysis, and we say, well, if I put my website to being blue, I get like an uplift of 179. If I use the red one, it's 156, and if I use standard, it's 150. So the conclusion is that the website here should have a blue background because it's higher than these two, for example. And then if we have the coupon activated, then we have a baseline sales for the total, which is kind of including these three parameters. But when we deactivate the coupon and we just do standard sales, you can see we lose 50 in value. So yeah, that clearly has an impact. So anyway, after we have the model, we can do all the analysis that we want. Then we look at the residuals. So these are the things that we might want to look at the residuals. The first thing that we have here is the residuals versus fitted. First thing that I want to pay attention here is that the variability of this shouldn't be increasing nor decreasing. It should be kind of stable. You can see that except for observations 132, 79, and 155, the variability of this seems to be pretty standard. That's good. If that doesn't happen, then we need to apply a correction because it means that these p-values that we have here are not statistically right. Then the other thing that we should look at is whether the residuals are normal or not. They seem to be normal. This is a cuckoo line. This line would show me where the residuals should be lying if they were normal. So you can see most of them are mostly okay. We have a few cases which makes me doubt, to be honest, and maybe an additional part. So yeah, maybe this is not normal. We'll see. If the results are not normal, then we still have some sort of problem here, because it means that these p-values are not valid anymore. The other thing that we look is that at the Cook's distance. So you can see that for these three cases, 155, 180, and 258, these Cook's distances are quite big. Usually we look at this and we compare against the mean. So the mean, I would say the mean here is probably, if I'm guessing, around 0.005 or something like that. So in these three cases, the values here are maybe 6 times over the mean. So they're quite big. And usually the rule of thumb is that if these values are 3 times greater than the mean, we should have a look. This means that these values having a large Cook imply that if we remove these observations, the coefficients would change a lot. So if we remove them from the model, these 3 would change by a lot. That kind of obviously casts some doubts over the quality of the model, because if the model coefficients really depend on 3 observations, we should be very careful. And finally, we can plot a histogram of the residuals, again, to try to see if they look Gaussian. It's very hard to see if these are Gaussian. These don't seem to be very symmetric. And yeah, here the left tail seems to have more than I would like to see. So I have some doubts whether this is truly a Gaussian residuals coupled with a cuckoo line, which I'm not very happy with. So you can use a Harkivera test. There are some tools that we can use to test whether the residuals are properly Gaussian. But anyway, let's assume they're Gaussian, and that's where we would end. Residuals are okay. Model seems okay, so we can make predictions for this model, and we can do inference and do analysis on the coefficients. That's really it. Now the Bayesian approach is completely different. The idea of this model is that instead of treating these coefficients that we have here, website blue, red, standard, and type standard, so these 4 coefficients, as actual fixed values that we want to discover, we will treat them as distributions that we don't know. So basically the way this works is like this. So we have a prior idea, like a density function for each one of them. And you can think of that as a probabilistic assessment on where we think the values are. So we think, well, they might be probably, it's very likely that the value for, I don't know, the red coefficient is 150. And we're pretty sure that it should be greater than 50. And it should be concentrated somewhat between 50 and 150. So that kind of determines some sort of shape for that distribution. So that's what we call a prior. We have a prior idea, a prior expectation. We load that into the model, and then we want to discover what happens when we update that prior with the data. And that's what we call the posterior density function. So just to show what I have here, what I plot here at the end are the posterior densities. So that is the same. We load the data, that this part is the same. Then we use a package, so we use the rstan package, which is the most famous one. And you can see that here I'm specifying the priors for the coefficients. So here I am specifying the priors. I put these priors, these are no. So I think that what I'm saying here is that I think that the coefficients for the first 3 are 100. That's my expectation. And then yeah, I'm leaving some room there because I am adding a 40 as the standard deviation. I don't know, but I am putting some 40 value, so that will imply that each one of the coefficients, you can think of them for me, that I think in my expectation there are some random variables centered around 100. And the same thing for the 4th coefficient, which corresponds to the type standard. I don't know what it is, so I'm putting 0. So maybe it's 0, maybe it's less than 0, maybe it's more than 0. And again, I'm putting some value here. We can put any distribution that we want here, the usual ones, and based on our knowledge of the situation. So if we are very certain about it, let's just say I was super certain the value should be around 100. In that case, I will put the standard deviation here to be very small. I put 2. That means I'm very sure. And then we need to specify these things that I won't describe here, but essentially the dimensions of my problem. If you have any doubt, just leave a comment there on the video and I will try to answer. And what we do there is that we pass this to stan, and that's really what we do. We obtain this first output that you can see here. These are the chains, so this is running Markov chain Monte Carlo. This is an iterative process that runs for a lot of time until the numbers kind of converge to what we call the stationary distribution. What that means from a practical perspective is that what we see here are the 4 chains, so this runs in each one of 4 cores in my computer. You can see them, the 4 of them plotted on top of each other. And ideally I would like to see what I'm seeing here, like some noisy thing that moves up and down without clear direction. If there was structure in here, then I would be very suspicious whether the stationary distribution was achieved. And finally, this is the final part. After we make sure these look okay, the convergence looks okay, we look at this report. This says what's the posterior mean. So the posterior mean for each one of the coefficients, you see it change. So it's no longer 100. And obviously for is it the red one or the blue one? For the blue one, we get the highest coefficient. And then we get the mean, standard deviation, etc. But these are distributions, remember, this is very important. These are no longer coefficients. And what we usually do there is that we plot the posterior mean. So there are several packages. The one I'm using here is called the bias plot that you see there. It allows us to plot the posterior mean with some confidence interval. The confidence interval word is probably not appropriate in a Bayesian context, but anyway. And this is where we would expect the mean to be lying at for that posterior density. So as you can see, this is the standard case, this is the red case for the website, and this is the blue case. And finally, we can plot the posterior density to just see the shape. I was assuming they were Gaussian, symmetric, standard ones, centered around 100. You can see that expectation changed. As you can see, for the standard one, it's still centered at around 100, which seems reasonable. For the red one, you can see it got displaced slightly to the right. So now the mean is, as I said before, is around 106. And then for the last one, the mean is probably around 129, which is what I had before. So these are the posterior distributions for the coefficients that I estimate. And this is important. Those coefficients are not fixed quantities, and I am repeating this again and again. These are random variables. And there are many interpretations for how we could treat this in a Bayesian context, but I think the easiest one is think of this as a subjective probability that you have in your head, that you don't know very well where the coefficient lies, and this is just an updated shape of how it would look like.